All right, so let's move on to talking about particle sizes and changing particle sizes. We started the column dimensions off with resolution, so we'll start particle sizes off with resolution as well. So if we decrease our particle size, we should expect to see an increase in resolution. The improvements in packing efficiency result in an increase in the column efficiency. By that I mean smaller particles pack more efficiently than larger particles do. And because smaller particles pack more efficiently, we will see an increase in the number of theoretical plates n. And as we talked about before with column dimensions and length, an increase in n results in an increase in resolution by the square root of n. As an example of that, here is a chiral pack IB3, so a 3 micron column, and compared to a chiral pack IBU, sub 2 micron, 1.6 micron column. The same column dimensions, so a 3 by 100 millimeter length column. If we were to pack the column and simply calculate the number of theoretical plates for chiral pack IB3, here you see that the number of theoretical plates is just a little north of 15,500. And for chiral pack IBU, it is almost 23,000. So there's an increase in the number of theoretical plates of almost 1.5. And that again has everything to do with the fact that these particles pack more efficiently, and therefore you have an increase in the number of theoretical plates. Going back to what we talked about in terms of improvements in resolution, the square root of 1.5 is 1.2, and so you do see roughly a 1.2 fold increase in resolution from 7.4 to 8.8. Now, to dig a little bit deeper, we can look at a Van Dienter equation to figure out what exactly is going on here. So we know that if we have a higher number of theoretical plates, we have an improvement in resolution. We also know that smaller particles pack more efficiently. So for the purposes of this discussion, we can focus in just on the A term, eddy diffusion, and the C term, resistance to mass transfer, as those are the terms that are directly affected by column packing and particle size. So eddy diffusion, A term, basically just describes the path at which the analyte has to travel through the column. That is shortened by a smaller particle. And the resistance to mass transfer is the way in which we describe the ability of an analyte to interact with the stationary phase and then come back off of that stationary phase. And the C term is diminished or decreased anyway for smaller particles. It's easier to interact and come back off of a smaller particle. Now you can see based on the shapes here of our Van Dienter equation that the A term basically sets the overall minimum of our plate height here. So if we have smaller particles, we would expect a smaller plate height. And the C term, the resistance to mass transfer, the slope of this line is shallower for smaller particles, meaning that as we increase our linear velocity of our mobile phase, we should expect to see a diminished loss of resolution. So in practice, if we look at what that looks like here, a Van Dienter plot of 10 micron, 5, 3, and 1.9 micron particles. The effect of the A term, as you can see here, for 10 micron, because you can't pack as efficient of a column in larger particles, has a plate height of somewhere around 0.02 millimeters, whereas your 1.9 more easily packed particles is well below 0.01. And of course, as we increase our linear velocity, we do see that expected loss of resolution for 10 micron and even 5 micron, whereas 1.9 is more or less relatively flat. So that's kind of why we can get the improvements in resolution with our smaller particles going faster, whereas we generally tend to lose that with our large particles. So if we look at pressure for a second here, as particle sizes decrease, pressure increases, assuming again that all other parameters are maintained. So going back to that pressure equation, we know that the change in pressure is inversely proportional to the particle diameter, so that all holds true. This, of course, can be counteracted by decreasing the column length or decreasing the flow rate, which we talked about previously when we talked about scaling for flow rates. Now, because we know we can push our columns, our small particle sizes faster and not lose any resolution, it allows us to generate something that looks something like this, where we might have had an older separation on a 5 micron chiral pack IA. The column dimensions here are 3 by 150. The resolution is certainly very good here. The flow rate is very modest as well, 0.425 mils a minute. Obviously, this could be increased, the flow rate could be increased, and we could probably shorten this analysis time a bit. However, keeping in mind what the Van Diemter curve looks like, we might also find a situation where we begin to lose resolution as a result of increasing that speed. But if we move down to a smaller particle size, 3 micron, for instance, here we can push them a little bit faster and not have any issues or less of an issue with pressure. So we can cut down our analysis time to 4 minutes. And of course, as we decrease the particle size, we're going to see an increase in the pressure. So we can also reduce our overall column length to a 100 millimeter length column, which will have an effect on retention time as well. And then take it a step further and move to our sub 2 micron columns. Here now, we really aren't expecting a whole lot of loss in resolution at all if we really increase the flow rate. So we're up to now 1.7 mils a minute. We have our retention time down to less than a minute, and we obviously have no loss in terms of the resolution, but we've saved ourselves a substantial amount of time, a substantial amount of solvent as well. This is extremely important, especially when you're looking for high throughput screening. So this is an example of a 7 compound library on 5 sub 2 micron columns. This is a screening that could be done in the course of 4.5 hours versus what traditionally had been done on 3 or even 5 micron columns, which would have taken at least overnight, maybe even into the next day to get these results back. So it's a huge time savings, especially when you're trying to screen as many columns as you possibly can, or as many compounds as you possibly can in one time. We talked about sample loading before. So sample loading, obviously smaller particles have less surface area, and so they can naturally only handle smaller injection volumes. So we would never be doing any kind of an analytical or any kind of a preparative separation on sub 2 micron or 3 micron particles. It just simply is way too inefficient. We would need to at least use 5 micron, maybe even 20 micron, depending on the scale. So larger particles and therefore larger column dimensions are much more appropriate for preparative scale chromatography. Now, back at the very beginning of the presentation, I mentioned that 5 micron kind of straddles this very interesting line where it's useful for both analytical and preparative scale. And what we see a lot of times happen is customers will develop methods on 4.6 by 250 millimeter length, 5 micron analytical columns. And what they will do is they know that it translates well into preparative columns based on these scaling factors that I have shown here, a 4.6 millimeter ID column to a 1, 2, 3, or 5 centimeter ID prep column of the same length, easily scales. And if you perform a loading study to determine the productivity in either milligrams or grams of material processed per hour, you can figure out what your loading is on your analytical column and then gauge pretty accurately what size column you need for the preparative scale separation that you're planning on doing. And so if we do what is called the touching band approach, we would perform an analytical injection such as this for this precursor of a calcium sensitizing drug. Very nice looking analytical injection. We would begin increasing the injection volume and we would achieve something that looks something like this, where in red is the most concentrated or the highest volume injection that we're making. It's roughly 20 milligrams of material on the column. And what we see here is obviously the tail of peak 1 is slowly approaching the front of peak 2. We might even be able to load more material on the column in this case, but it demonstrates the point that we're loading more and more and more on the column. And so we can calculate our productivity and figure out, especially if you're buying a new column, what size do I need given the scale that I'm trying to separate. All right, and lastly here, we'll finish with our conclusions. We're almost out of time. So what should I choose? Up to this point, we've basically just been talking theory, but in practice, the question is what column dimension, what column particle size should I be using for my separations? Now, these recommendations that I'm going to make you are not hard and fast. They are what we internally do and what collectively as the DyeCell community we've established. But for your given separation, you might find that you can get away with a smaller length, a shorter length, or a smaller ID or a smaller particle size. It really depends on your separation. But in practice, what we recommend for analytical HPLC, typically we're going to be utilizing a 4.6 millimeter ID column of either 150 or 250 millimeter length. And as far as particle size goes, either sub 2 micron or 3 micron. Now for the sub 2 micron columns, as I have marked here, they are currently only available in 3 millimeter ID and limited to either 50 or 100 millimeter length columns. Not that big of a deal, but something to be aware of. We can custom pack longer length columns if you so choose, but that's what is more or less commercially available at the moment. Now, again, like I said, this can change. This really depends on your separations. 5 micron, as I mentioned, is certainly useful if you're planning on transitioning to preparative scale. But if you're just looking for analytical only, then 3 micron is a good way to go. For faster screening, you can certainly look at doing a 50 millimeter length column, but there is a higher likelihood that you might miss a separation if you go that direction. So when we do our screening internally, generally we're always screening on 150 millimeter length column just to kind of minimize the chances of us missing something. For prep HPLC, as far as utility goes, most people are utilizing either 2 or 3 centimeter ID columns of 250 millimeter length. Particle sizes for HPLC, either 5 micron or 20 micron, depending on the scale. Most people don't use 10 micron anymore. You can get away with 5 or 20. Both of them kind of serve the role that 10 micron used to. We can use a 150 millimeter length column if you are operating near or at the system pressure limits and you have concerns about potentially going over pressure. Obviously, decreasing the column length will help with that issue, but you might have to do some optimization, obviously, in going to a shorter column. For SFC, for analytical SFC, typically you're utilizing either a 3 or a 4.6 millimeter ID column of either 100 millimeter or 150 millimeter length. Again, that doesn't mean that you can't use a 250, but generally speaking, most people are screening, especially with 100 or 150 millimeter length. Particle sizes are the same, either sub 2 micron or 3 micron, and 5 micron if you're planning on doing any preparative scale work. For faster screening, you can, again, get away with a 50 millimeter length, but you might miss a separation possibly. For prep SFC, same length, I should say, 250 millimeter, and same column IDs, 2 or 3 millimeter. Particle size, though, is typically only 5 micron. 20 micron does not get used very often for SFC separations. Generally, it doesn't need to be, because you have a lower viscosity of your mobile phase. Even though you would expect higher pressure on 5 micron, generally it's mitigated by the fact that your viscosity of your mobile phase is much less. And again, you can use 150 millimeter length column if you're operating close to system pressure, but it's not necessary and could potentially require some optimization. Well, that is all I have for you today. It was a very brief discussion, I know. So if there are other questions that you have related to this issue, or like I said at the beginning, if you have specific questions about your separation that you'd like us to help you with, feel free to email us at questions@cti.dicel.com for general column chromatography or method development questions. Feel free to email me directly about this presentation or about any chromatography or column questions that you might have as well. I do monitor the questions email address, so chances are I will see a question either way. We do have a number of webinars that we've done in the past. We have a chiral method development, a sub 2 micron column care, and method validation series that we've performed. And we have 2 more coming up this year, one in July and one in November. The topics are currently to be determined, but one of them will probably be a repeat of the chiral method development talk that we gave previously. But we're always open to your suggestions, so feel free to shoot us an email and let us know what topics are interesting to you and what you might want to see us discuss further. At this point, I have nothing else for you, so I would like to thank you again for tuning in today. We really appreciate your attention. We're always looking forward to helping you as much as we possibly can. So please don't hesitate to contact myself or questions or your sales rep, and they'd be happy to help you in any way that we can. For myself and from the rest of the Dicel family, especially here at Chiral Technologies, we wish you and your family the safety over the next few weeks and months as everything begins to develop here in our country. Let us know how we can help in any way. And again, we appreciate your time today. So stay safe out there, and we will see you next time.